Section 7.1. This is about, the entire chapter is about sampling distribution of the sample mean. Just to recall from before, we have, so what happened is this. In statistics, we don't have access to the entire population. So what do? We work with samples. We study the samples, we analyze them, and we try to draw conclusions from the sample about the entire population. That's what we do the whole time. So what we do is we used to recall x bar is the sample mean and mu is the population mean. The sample mean, the sample with size n, small n, always we use always small n for the sample size. The population size is capital N. So that's important to recall because we're going to be using this. So what happened here is this. We still don't have access to the entire population. We're going to pick a sample. We're going to study the sample, draw conclusions about this, and from the sample about the entire population. But what you're doing here, you are approximating. There's an approximation. So this approximation will cause an error within the sample. So that's what sampling error means, or that's where the name came from. So the distribution of all the sampling errors will be shown here in this section. So what we need the sampling distribution for is we are going to take within one sample or within a population, we pick samples and we find the mean for each of these samples. Okay, and then we try to see, if we look at the mean for the entire population and the mean for all these samples, how different is that going to be? Would that be a lot or small, or it's exactly the same? So we will see this, and then at the end we're gonna see what happened as we increase the sample size. Okay, as the sample size increases, what happened to the sampling error? What's gonna happen? So again, sampling error, as you can see here, is the error resulting from using a sample to estimate a population characteristic. That's what the sampling error is. Resulting from using a sample to estimate population characteristics. And so here what we have is we are going to do sampling distribution of the sample mean. So each sample we're gonna pick, we're gonna find its mean, and then we're gonna look at all these means. So it could be like x bar 1, x bar 2, x bar 3, all the way to x bar n. So these are different samples. That's the mean for the first sample, mean for the second sample, third sample. And then we're going to convert these means to the population mean. And let's see if they are the same, different, and how different is that? How spread is it away from the population mean? Okay, so to do that, let's look at this example here. We got 5 players. We named them A, B, C, D. And the height of each player is, the first player has 76 inches height. Second one 78 inches height, 79 inches, 81 inches, 86 inches. And then what we did, we took on the left side in the table, just focus on the table for now. We took them pairwise. So we took A with B, A with C, A with D, A with E, then B, C, B, D, B, E, then C, D, C, E, and then D, E. There's 10 possibilities, as you can see. Now the heights that we see, 76, 78. The next one, A was 76, C 79. A is 76, D is 81, and so on and so forth. And then we found the mean, x bar, the mean for these two. So you add these two, divide by 2, you get 77. Add these two, divide by 2, 77.5. Add these two, divide by 2, 78.5. So we got the mean to all of them. And I'm gonna come back to that in a minute. So this is my entire population, which is really the small of it. It's very small. It's only 5. So what are we gonna do? We're gonna find the population mean mu by adding all these numbers in the first table, divide by 5 because there's 5 players, and then that gives me 80 inches. Now, if I look at the number I got here, the 80 inches, and the mean for these pairwise heights, I see there's only one of them that matches. The rest are either a little bit less or a little bit more. So out of 10, there's only one of them. So the chances that the sampling mean distribution is the same as a population mean was only 1 out of 10, as you can see, or 10%, right? If you multiply by 100, that's 10%. So this means that because there's only 10% chance that the sampling distribution will be mean, will match with the population mean, that will cause what we call sampling error. Sampling error. So I said sampling error may occur. So this is the sample of size 2. So I paired them wise 2 at a time. Can we do 3 at a time? Yes, we can do every 3 at a time. We can take every 4 at a time. You know, we can take it 1 by itself, then 2, every 3, every 4, and maybe all of them together, like 5. And then see what happens. But before we move on to that sampling distribution, let's look at taking these points and plot them on a dot plot. So we construct the dot plot, as you can see here in green. The green number 80, that's this number here. That's the population mean. And we plotted the points. So the first point on the table here was 77. You know, this one 77, then 70 something. So we plotted them here, 77, 77 point something, and then all the points. Now there's only exactly one point, as I told you, that matches this. But sometimes researchers like to look at within 1 unit or 1 inch from the population mean, how many points are there? Well, if you go up 1, there's this one. If you go down, there's 1. So in total, within 1 inch from the population mean, there are 3 dots out of 10. So 3 out of 10. Okay, so the ones that I circled, 3 out of 10. So we can say 30%, that shows that the dot plot shows that 30% the sampling error made in approximating mu by x bar will be less than or equal 1 inch. So if that makes sense. So that's within 1 inch. If you want to go 2 inches, you can count how many points divided by 10. 3 inches, number of points divided by 10. And then you multiply by 100. So if you have 3 over 10, you want to convert to percents, all you have to do, multiply by 100 and put the percent sign. So this 0 cancels. You get 3 times 10%, which is 30%. That's where that came from. Now, what happened, as I said earlier, if we do n equals 1, the size of the population is only 1. So if the size of the population is 1, what we do in this case, we can see that you don't have to pair them at all. You just plot them, the given dots. So this is the mean, which is 80. Okay, so you just have to plot them on the graph, and you see there was 5 points. When we paired them 2 at a time, that's the one we showed you earlier, we got these points. If you do 3 at a time, like you do ABC, ABD, BCD, ACD, then you will get these dots. If you do 4 at a time, you do ABCD, ABDE, or something like that, like you just list 4 at a time. And then 5 at a time, there's only 1, because there's only 5 of them, A, B, C, D, E. So then you get only 1 dot. So what happens is, when it was 1 case, look how the points were spread. This away from the vertical line. That's the mean. That's the population mean. Then when we increase the size to 2, these dots start getting closer to each other. Even more close, more close. You end up with 1. So that tells us, as we increase the sample size, the smaller we get for the sampling error, or the sampling error tends to be. So we wrote that they give you the percentage here if the sample size, what happened here if you increase the sample size, and this is the number of possible samples. Here's only 1 sample. The one we did for 2, we got 10 of them, if you remember, A, B, A, C, A, D. And within 1 inch from the population mean, there were 2 dots, 3 dots, 5 dots, 4 dots, 1 dot, or 1 point. And then here that represented 30%, 40%. We calculated this earlier, 30%. I showed you how. But if you go to the last one, it's 100%. It's like really there. So and then here they just tried to do it, within 1 inch or 2 inches or no inches, and then But you see, this is the main result here, that the larger the sample size, the smaller the sampling error tend to be when it comes to estimating a population mean by using the sample mean. That's what this section is about.